Hey class, welcome back. We're taking a look at continuing on with Unit G on graphs and tables and looking at how to determine class boundaries and class marks for the classes that we set up using Sturge's method or intuitively. So we want to define a couple of things here. First of all, class boundaries. Class boundaries are the highest and the lowest values in the class. And it's important to know that if we were to take a look at, say, class exercise number 3 here, the ages of 50 people, and we want to look at class widths of 10, we don't set them up this way, 0 to 10 and then 10 to 20 and 20 to 30. And the question is, well, why? And hopefully the answer is obvious to you, is that, well, if you have somebody who's age 20, which class do they fit into? Is it the 10 to 20 or the 20 to 30? So instead, what we're going to do is we're going to set them up as 0 to 9, and then 10 to 19, and 20 to 29, and so on like that. The class mark is a single number which is most representative of the values in the class. Usually it's the midpoint of the class, but it isn't always the midpoint, and I'll show you some examples of where that's the case. The midpoint is just simply found by averaging the class boundaries. So if you have a class, say 60 to 69, then you would just say 60 plus 69 divided by 2 gives you 64 and a half. And so when we're talking about the ages of people in our group, then we can think of the 10 people in their 60s as having an average age of 64 and a half. That will become more obvious when we get into calculating grouped means and things like that later in the next unit. Okay, so let's take a look at how we do that. By the way, the symbol M is what we'll use to represent the class mark. Sometimes I'll refer to it as the midpoint, but that's just kind of a lazy way of saying it. It usually is the midpoint, but it's really the class mark that we're talking about here. So let's calculate the class marks for each of the examples below. And are there any tables where the class mark either can't be calculated or has no meaning? So I want to give you a couple of other terms here. Discrete and continuous data. So discrete nominal data and discrete ordinal or interval data, and we've talked about the difference between nominal, ordinal, and interval data, but the word discrete means that it's countable, as opposed to continuous data, which are measured. So we want to start here where there's only one possible value in each class. So when I take a look at, for instance, the ratings of TV shows for our 80 students, and I want to find out how many gave the movie a rating of 1, how many a 2, how many a 3 and 4, and so on, all the way up to 10, then the class mark in this case is really easy. What's the number that best represents the ones? Well, 1. What's the number which best represents the 2s? 2. And so on all the way down. So when you've got a single number here, then it's really easy to do it this way. If we were to take all of our data, and let's say we had a couple of 1s, and then we had 3 2s, and then we had 2 3s, and then we had 5 4s, and so on like this. And if we were to do that and put all of them in a big line like that, so that there's all 80 numbers there, then what we're saying here is that the best number that represents the 1s is 1. The best number that represents the 2 is 2. So these are the class marks then of those numbers. So it's trivial in this particular case. It's trivial in the next example too. Now when we're talking about ages is different from TV show ratings, which is what kind of data? Well, it's ordinal, right? Ordinal data are data where the numbers are ranked, or in this case, rated. But when you're talking about ages of kids, then we're talking about not nominal, not ordinal, but interval data. And in this case, we would say it's ratio data, although we'll tend to stay with interval data, and that just simply means that the difference in age between a 10-year-old and an 11-year-old is the same amount as between an 11-year-old and a 12-year-old, and the same amount as between a 12 and a 13-year-old. Okay? So the question is, what is the number which best represents the ages of all the 10-year-olds in the class? 10 is trivial, and 11, and then 12, and then 13, right? Let's take a look down here at the next one here, where we're saying, we're talking about gender. So we've got males and females. We could have other two, but what's the class mark in this particular case? Well, here's a case where you're dealing with nominal data. It doesn't really make sense. So, I mean, we could assign numbers here. We could call the males 1 and the females 2, or we could call them 0 and 1, or we could call them the square root of minus 3 and pi. I mean, it doesn't really matter what we call them. The most important thing here is that we've got two classes, and what we typically do is just simply denote them by their names, M and F. So there's no class mark here. There's no number which represents them. When we get into the end of 307, we'll have something called dummy variables, and that's where we will assign numbers of 0 and 1 to them. But at this point, we're not interested in that. All right, those are trivial examples. Now we're going to take a look at discrete or ordinal data, interval or ordinal data, where there's a few possible values in each class. So these are the kind of problems that we've been working through in class. So in this particular case then, we would look here and we would say, okay, what's the number which best represents anybody in the age group from 0 to 9? And we would say, well, let's see, 0 plus 9 divided by 2 is 4.5. So the class mark is just the midpoint of that class, which is 4.5. 10 plus 19 divided by 2 is 14.5. And then we've got 24.5, and you can see the pattern here. So these become the class marks, which are just the midpoints of the classes. And we'll see where that becomes useful when we get into doing calculations such as, suppose I want to know what the average age of everybody is in Red Deer. Well, I can just simply take a look at the class marks and then their frequencies and do some simple calculations here. By the way, the last one here, if you take 90 and 100 and add them together and divide them by half, you'd get 95. You could use that. I would probably just follow the pattern here. Either one would be correct here, and so it doesn't really matter. From a mathematical point of view, you find that it'll make almost no difference here. All right, let's take a look here at the next one here, where we're dealing with continuous data. And continuous data is where there's many possible values in each class. So when we're talking about things like height or weight, we can actually measure somebody to the nearest millimeter. We could actually measure them in height to something less than that, although it's trivial in that particular case because, of course, people tend to rise and fall with the way that they breathe. Of course, their hair takes up a certain amount of space and so on like that, and so it's kind of trivial. But theoretically, we could do it to the nearest millimeter or 10,000th of a millimeter if we want to. The same sort of thing with income is that although we tend to round it to the nearest dollar, if you're dealing with, say, Revenue Canada, you'll probably round it to the nearest penny. And then even in terms of, say, interest calculations in a bank, I mean, it might come out to parts of a 1/10 of a cent or 100th of a percent, but there you would still round it to the nearest cent. I'm just going to close the door here. But it's still continuous in the sense that what's the difference really between somebody who makes $19,999.99 and somebody who makes $20,000? Well, it's a penny, and I mean, we don't even carry pennies anymore. So it's virtually nothing. And so The way that we handle that is where there's a large number of values in each class is we consider the data to be continuous, even if we tend to, by practice, we tend to round it to the nearest cent or dollar or even $100 or even thousands of dollars depending on the type of data, right? So what we would do here is we would say, well, I actually want to jump down to the second one here, and you'll see why in a moment here. The class that goes from 20,000 to just less than 30,000. What we do is we think of 30,000 as being the practical upper limit, even though it's 29,999.9999999 if it's continuous data. But we think of 30,000 as being the practical upper limit. So we average those two out. 20,000 plus 30,000 is 50,000 divided by 2 is equal to 25,000. So we've got 25,000 there. Next one, 30,000 to 40,000. Midpoint, class mark, is the midpoint of the class, which is 35,000. Then we've got 45,000. And we've got 55,000. Now, what do you do with the last one? So here's a case where you can have income which is billions of dollars if you're Bill Gates. And so what do you put down then for a class mark? Well, what you do is you assume the pattern here. So you assume a practical upper limit of 70,000. And so we would put down 65,000 here. Now, similarly, when you're going down this way, then what you typically do is you assume the same pattern going down. And so you would think of a practical lower limit of being 10,000, in which case you would make this 15,000, which is halfway between 10,000 and 20,000. So when you've got open-ended classes, open-ended meaning that it's anything upwards, or if you have particularly a first class that is, let's say 0 as a lower bound or something really small, then you would put down 15,000. You would, use the same pattern. So use 10,000 as a practical lower limit. Just as an aside, we're going to see this a little bit later, but something that we'll look at is the weights of business students. And what we'll find is that the lowest weight is somewhere around 82 pounds, I think it is. So we're going to have classes of 20. It's going to go 80 to 99 pounds, and then we're going to have 100 to 119 pounds, and 120 to 139 pounds, and so on like that. You may actually choose to write this particular class as less than 100. Now, if you were to do that, you wouldn't choose as a class mark 50, because you don't have any college students that are near the 0 or 10 or 20 or 30 pounds or even 50 pounds. I mean, they're likely to be at the high end of that scale. And so what you would do then is, if this first class was less than 100 pounds, you wouldn't choose 50 as a midpoint. You'd follow the pattern down and choose 89.5 as the class mark. Okay, so we're going to get to that a little bit later when we see that particular example here. Lists several things that you should keep in mind when you're constructing class boundaries. And I've got a list of a few things here then. And so you want to make sure that class boundaries don't overlap. Okay. Class marks are usually midpoints, but for open-ended and first classes of different widths, what you do is you follow the pattern. Okay, what do we have here as well? Try not to have too many classes of zero frequency. Now, we haven't really defined frequencies yet. That's actually in the next part here. Frequencies are just counts. That probably means that you've got too many classes, right? Or it might be the result of outliers, that sort of thing here. Okay? And so what you can do is you can list outliers if you've got some very high values or some very low values. Okay, what else do we have here? Yeah, I think that's pretty good. So those are the main things that we talked about. Determining the class frequencies. So finally what the statistician does is he or she they count the number of values that actually fall in each class. And the symbol that we're going to use for that is F for frequency, and then N is the total number of values in the data set. A relative frequency is where you take an F divided by N, and so that's just actually really a percentage of the total, and we'll see that as we go down here. So it's expressed as a decimal value or a fraction or a percentage between 0 and 1. Cumulative frequencies are found by summing up the absolute frequencies of any given class and all other classes preceding it. So the cumulative frequency tells the statistician how many values are less than or equal to the upper bound of that class. This is called a less than cumulative frequency. I'm going to show you an example below. A more than cumulative frequency is the opposite. What you do is it takes a look at the frequencies of all classes succeeding it. So it tells the statistician how many values are greater than or equal to the lower bound of the class. Unless specified when we talk about cumulative frequencies, we assume that they're less than cumulative frequencies, and the symbol that we use is CF over N. Finally, if you divide CF, if you divide CF divided by N, then you get a cumulative relative frequency. All right, let's take a look at how that all goes together here. So we're going to take a look at the ages of the 50 people. So I've reproduced it here in exercise number 6. Here's the 50 people. We've got our classes, and we used Sturge's method to figure out that we should have class widths of 10, and we don't want them to overlap, so we're going to have 0 to 9, 10 to 19, and so on down here. Now, you might say, why didn't we start at 10? And the answer is, well, absolutely, we certainly could have, except that you can be sure that if you put down a table and you don't show 0 to 9, then somebody's going to ask where it is. And so all you do is you put down that class, and then you put down the frequency of 0, that there's nobody in that class. All right, so let's take a look at the class marks first. And we've done this already in a previous page. So 0 plus 9 divided by 2 gives you 4.5. And then 10 plus 19 divided by 2 is 14.5. And then we've got 24.5. And again, this is something that we just did. And I'm just following the pattern down here. So 90 plus would be 94.5. Now the actual frequency here is where you just do a count. So these are all ordered, so it's really easy to say that there's nobody in the first class. There's no 0 to 9s. And then we've got one value here, 114, so that's going to be a frequency of 1. And then there's 1 in the 20s and 1 in the 30s, and then there's 2 in the 40s. That's these two guys right here. And then we've got 1, 2, 3, 4, 5, 6, 7 in the 50s. We've got 10 in the 60s, 12 in the 70s, 10 in the 80s, and then 6 in the 90s. Here's the 90s, 1, 2, 3, 4, 5, 6, right at the very end here. Okay, that's these guys. So what we've got is our midpoint, or class mark, the absolute frequency. Now let's take the relative frequencies and divide through by n. If you sum up these absolute frequencies here, you're going to get 50. So that's our n. And so if we divide each of these by n, so 0 divided by 50, 0. 1 divided by 50 is 0.02, and so on. And we can go down the whole thing like this. All right, 12 divided by 50 is 0.24. And by the way, those will add up to 1, or 100%. All right, next column, the cumulative frequency. This is the less than cumulative frequency. And what we do then is, I'm gonna just change colors here. I'll go to maybe purple. And so what we do is we start with this number here, 0, and then we're going to add this number, 1, and then we're going to add this number, which is 1 plus 1 is 2, plus 1 is 3, plus 2 is 5, plus 7 is 12, plus 10 is 22, 34, 44, and 50. And by the time you get to the end of the last class, you got to be up to n. Now, let's divide each of those by 50. So 0 divided by 50 is 0. And then 1 divided by 50 is 0.02, 0.04, 0.06, 0.10, 0.24, 0.44, 0.68, 0.88, and 1.00. Now the cumulative frequency more than cumulative frequencies, I'm going to change color again, I'll go to green, is where you actually start down here and you work up. So you go, oops, there we go. So we go like this, 6 plus 10 is 16, plus 12 is 28, plus 10 is 38, plus 7 is 45, plus, what am I up to, 2 is 47, 48, 49, 50, and then plus 0 is 50. Whew. Now let's divide each of those by n, which is 50. So you're going to have 1.00, 1.00, 0.98, 0.96, 0.94, 0.9, what is that? 0.76, 0.56, 0.32, and 0.12. Let me just check all those numbers, because sometimes I get my numbers wrong. Yeah, that looks good to me. Good. So that's what we've got. Now, last thing I want to show you here is, so what do each of these numbers mean? Well, let's highlight. And we'll highlight in maybe a yellow or something like that. So, what does this number here mean? 7. The absolute frequency of 7 says that there are 7 people in their 50s. Okay? And you can see them all here. There's right there. 1, 2, 3, 4, 5, 6, 7. All right. How about this number here? The 0.24 means that there's 24% of people in their 70s. Now we get to the less than cumulative frequencies. Let's take a look at this guy right here. Now the definition that we had here was that is how many values are at the top of the page here are less than or equal to the upper bound of that class. Now the upper bound of that class is 69. So we would say that there's 22 people who are 69 or younger. Okay. Now let's take a look at another one. How about this one here? This is the same number basically, but different class, but in a percentage. So 88% of people are 89 or less in age, less than or equal to the upper bound of the class. Okay, let's go over here and choose maybe that guy here. Now this is a more than cumulative frequency, and it says, up at the top here, tells you how many values are greater than or equal to the lower bound of that class. So the lower bound of that class is 50. So we would say that 45 people are 50 or older. And if you take a look at that, you'll see that that includes everybody except for the first 5. Just take a look over here. I should change that back. Right? Take a look over here then. And except for the first 5 people, everybody else then is 50 or older. Okay? And finally then, let's take a look at maybe this guy right here. This 70.76. The lower bound is 60. And so we're saying that 76% of people are 60 or over. So that's how we read all these numbers here. I'm going to leave for you this one for homework, so I want you to fill that in, and then we will take that in class. If we don't get to it in class, then I'll post it. And that ends the lesson. After that, we're going to go into graphs.